Hello everyone. So in this video I'm going to be explaining the molar volume applied, the molar volume, which is the mole applied to gases. Right now the first thing we need to know is a little bit about Amedeo. And we've seen the word Amedeo Avogadro, or we've seen Avogadro's number already, which is simply just 6.02 times 10 to the 23rd power. Right, I'm sure we're all familiar with Avogadro's number. Right now, Amedeo Avogadro, after whom we named the Avogadro's constant, is he was the first to suggest that a molecule was the smallest particle of a gas that could exist independently. Right? He also defined the atom as the smallest indivisible particle of an element that can take part in a chemical change. He did not, however, work out the number of particles in a mole, which was done by Jean-Baptiste. Now, what this is all saying is that yes, Avogadro made some significant contributions. Right? He said that the molecule is the smallest particle that can exist, the smallest particle of a gas that can exist independently, which is on its own. And he also said that the atom is the smallest indivisible particle, right? But he was not the one who discovered the number of particles in a mole. Right now, let us just continue a little bit. Something a little bit more about what Avogadro discovered was his own law, which is Avogadro's law. Now, his law says that at constant temperature and pressure, equal volumes of a gas will contain equal number of molecules. Now, what that is saying is this, right? No matter the temperature, no matter the temperature or the pressure, right? And no matter the type of gas, equal volume will always contain equal number of molecules, which is, remember that molecules relate to particles, so equal number of particles. For example, let's say I have these two balloons, and I love to use the balloons example. Right, I have these two balloons at 25 degrees Celsius and 1 atmospheric pressure, 1 atm. Right, now this balloon contains oxygen gas and this balloon contains hydrogen gas. The balloons, we're going to say they are the same volume. We're going to say they have a volume of about 5 cm cube. Right, they're both 5 cm cube, so it's the same temperature, which is 25 degrees Celsius, the same pressure, which is 1 atmospheric pressure, and the same volume. Right, and so therefore we expect that in these balloons it's gonna be the same amount of particles of these gases. So let's say this balloon has 5 oxygen gas particles and this balloon has 5 gas oxygen particles. So this is what Avogadro's law says. It says no matter the temperature or the pressure or the type of gas, right, they will all have the same volume, right? And that is if they have the same temperature. So if they have the same temperature, the same pressure, right, different types of gases will have the same volume. So if I place another balloon here with helium gas, it will still have 5 molecules or 5 particles. Note that, however, if we increase the temperature, right, if we increase the temperature of our gas, so let's say it moves from 25 degrees Celsius to 30 degrees Celsius, the temperature is increased. Once we increase the temperature of a gas, the kinetic particles of the gas, or the kinetic energy, of the gas increases. The particles begin to move a lot more quickly, and so they expand. There's some expansion happening, and we expect the balloon to get bigger. So if we increase the kinetic energy of a balloon, if we add some heat energy to a balloon, right, or to a gas, we expect the particles to expand, and so the volume would increase. Just note that temperature does affect the volume of a gas, right? And I'm going to put that in writing so that we can have it. Let me just type it here. Oops. Let me see if I can add my... If the kinetic, or if the heat energy... Alright, so if heat is applied to a gas, the particles will gain kinetic energy. They will begin to move quickly, and thus they expand, which increases the volume of that gas. And note that if the pressure of a, or if pressure is increased, the volume of a gas will decrease. All right. Let me just put this. Okay. Nice. All right, so we have that little note right there. Yes, if heat is applied to a gas, the particles will gain kinetic energy. They will begin to move quickly, and thus they expand, which increases the volume of that gas. If pressure is increased, the volume of a gas will decrease. And this is just a little bit of physics and chemistry combined, and how pressure relates to volume, right? But we won't be looking in detail about this type of calculation. We're gonna go into the mole concept and how it relates to gases, right? Now for that, yes, so I hope we understand Avogadro's law, right? Just a recap for Avogadro's law. He says that no matter the temperature and the pressure and the type of gas, right, it will have the same number of molecules and the same volume. This is it in definition. At constant temperature and pressure, equal volumes of all gases will contain equal number of molecules. Right? Nice. Now this diagram here, it shows a little bit about how volume and molecules relate. So as you can see over this side, we have a low volume, right? A low volume. So let's say this volume is about 3 cm cube. That's the volume of our gas right there. It would have less molecules, right? But over the other end, over the right side, let's say this volume is 6 cm cube. As we can see, it has more molecules, right? So that's how the volume relates to molecules, and this gives us a little equation which says that the volume, I'm going to write it here, volume is directly proportional to the number of molecules. So as the volume increases the number of molecules, we expect that to also increase, right? Now we're going to look at the molar volume because this leads us into our calculation. This is what I just said. Volume is directly proportional to mole and also the molecules. So for molar volume, the definition is in it. It is the volume Molar volume is the volume of a gas that contains 1 mole of that gas. Molar volume, the volume of a gas that contains 1 mole of that gas. And this value is the same for all gases. See how Avogadro's law comes back in? This value is the same for all gases under the same temperature and pressure. And for these calculations, we're only going to be referring to 2 types of conditions, right? And these conditions have, of course, the same temperature and pressure, right? So for the conditions, the first one is room temperature and pressure. For room temperature and pressure, we know that room temperature is 25 degrees Celsius and the pressure is 1 atm, right? For any gas that is at room temperature, for any gas that is at room temperature, it will occupy a volume of 24 dm cube. For any gas that is at room temperature, it will occupy a volume of 24 dm cube. So if we have oxygen gas, right, at room temperature, it's gonna have 24 dm cube. If I have hydrogen gas at room temperature, it's gonna have 24 dm cube. That's how Avogadro's law comes back in. Remember, same temperature and pressure. The next condition that we're looking at is standard temperature and pressure, STP for short. Now for standard temperature and pressure, it's 0 degrees Celsius and it's also 1 atmospheric pressure. Right? Now for this, at standard temperature and pressure, all gases will occupy 22.4 dm cube. So you need to remember these. So at RTP, gases will have a volume or occupy a volume of 24 dm cube, right, for 1 mole. And this is all 1 mole, of course. And at STP, gases will occupy 22.4 dm cube. I'm not able to write it there. Right. So just remember these important values. And let us go into our first calculation. Right? The first calculation deals with if we're solving for the volume, right? So let's say we need to solve for the volume of a gas. The equation that we're going to be using is, let me erase. Right, so volume of a gas is equal to moles times conditions. This equation you need to remember for everything. This is one of those equations that comes back all the time on the mole concept. It comes back in energetics, it comes back in electrolysis. Once you know how to calculate the volume of a gas, you are good to go. So this equation is important. Volume of a gas is equal to moles times condition. Volume of a gas is equal to moles times condition. Right? And sometimes for moles, I'm just going to insert this right here. Just remember, just a little recap. Moles, there are 2 equations for moles. Moles is equal to mass divided by molar mass. And moles is also equal to number of particles. Guys, don't mind the writing, please. Number of particles, let me get this smaller, over Avogadro's number. This is going to come back. Just a little recap. Alright. Because sometimes you don't see the mole in the question. You have to solve for it. Alright. Okay. So for volume of a gas, it's equal to moles times condition. I'm going to write a question here before I solve number 1. So my question is, calculate the volume of hydrogen gas in 0.5 mole at STP. So it's a simple question, right? Very simple. Calculate the volume of hydrogen gas in 0.5 mole at STP. And let me just grab my calculator because I'll be finding this out as well. All right, let us go. So for this one, remember volume, once you say volume of a gas, you are going to use the equation volume of gas is equal to mole times conditions. That ST should be STP. Right, so the mole that we're given in the question, we're calculating the volume of hydrogen gas. The mole we're given is 0.5 mole. So 0.5 mole times the condition. The condition, it's STP. And remember that at STP, all gases will occupy a volume of 22.4 dm cube. Right, and now we solve. This answer is going to be 11.2. For the unit, it won't be mole per dm cube because for gases we don't use mole per dm cube refers to concentration. For gases we don't use that unit. Since we're solving for volume, the unit that you're going to simply use is dm cube. That's the only unit that relates to volume, so it's dm cube. So the answer is 11.2 dm cube. If we were to calculate the volume of hydrogen gas at RTP, we would simply just put 24 dm cube right here and we would solve for our answer. Right? Now, a simple note is that for our conversion, you need to know this. Well, 1 dm cube is equal to 1,000 centimeters cube. So if you needed to convert cm cube to dm cube, you would divide by 1,000. And if you need to convert dm cube to cm cube, you would multiply. So if you're going that way, you multiply. If you're going, let me put my division side. If you're going from centimeter cube to dm cube, you divide by 1,000. All gases are diatomic. This is very important. All gases are diatomic. Hydrogen gas is H2, oxygen gas O2. The only ones that are not diatomic is the ones, our noble gases. So helium, neon, xenon, those are not diatomic. They're monoatomic. They exist as one. So Hene. Right, but the others, all the others, nitrogen, hydrogen, oxygen, all of those are diatomic. Just bear that in mind because we're going to have to do some calculations relating to that. So let's go to our first big person calculation. So it says, what volume is occupied by 8 grams of hydrogen gas at STP? What volume is occupied by 8 grams of hydrogen gas at STP? So we need to calculate the volume, right? And we know that the volume of a gas is equal to moles times condition, right? However, we were not given the mole in the equation. We were given the mass, right? And the equation for mole that relates to mass is mole is equal to mass divided by molar mass. That's the only equation that we can use with mass to solve for the mole. So let us work it out. Right? So it says mole equal mass divided by molar mass. And for mass, the mass that we got was 8 grams. 8 grams of hydrogen gas, right? I remember that all gases are diatomic. All gases are diatomic. So hydrogen gas is H2. We need to solve for the molar mass of H2 gas. We have 2 hydrogens present, so it's 2 times 1. The molar mass of 1 hydrogen is 1 g mole. So therefore, it's going to be 2 times 1 g mole, which gives us 2 G mole. This is something that you always have to look out for. Yes, so the molar mass that we're going to use is 2 G mole. And now we can apply our condition. The condition is STP. The value of STP, or the volume of a gas at STP, is 22.4 dm cube. Right, and now we solve. So let me take out my own calculator and we're going to solve together. So it's 8 divided by 2 times 22.4. This gives us 89. See if I can get some space here. 89.6. Note that gram will cancel gram, yes, and since we're solving for volume of a gas, the unit is still going to be dm cube. I hope we got this one. Yes, let us work another one. For this one, it's solving for molar mass. This is gonna be like one of those complicated ones. Let me see if I can find another before I move on. Yes, I'm gonna give a question actually. So it's calculate the volume of a gas. Calculate the volume of hydrogen. Let me use oxygen gas, of oxygen gas in 4.24 times 10 to the 23rd power particles of that gas at RTP. Okay, so for this one, we need to calculate the volume of a gas. Once you see volume of a gas, always write your equation. Volume of gas, and this is oxygen gas, is equal to volume of gas equals mole times condition. Nice. Now let us work and look at our question. Actually, in the question we were not given, yes, we were given the conditions, but we were not given the mole, right? And we were given the number of particles. The only equation that we have that relates to number of particles is mole, and this is how the mole relates to particles. Mole is equal to number of particles divided by Avogadro's number, right? So we can use that equation. Let me just apply it here. It says mole equal number of particles divided by Avogadro's, spelling this wrong, Avogadro's number. Alright, so for the number of particles that we got in the question, it was 4.24 times 10 to the 23rd power. 4.24 times 10 to the 23rd. And Avogadro's number is 6.02 times 10. Let me fix my point here. Times 10 to the 23rd power. The condition that we got, which was, I think it was RTP. Yes, it was RTP. Don't mind the writing, guys. Please bear with me. So the condition that we got was RTP. RTP is RTP 24 dm cube, and now we can solve for our volume of the gas, right? Let me just insert here that the number of particles, since it's a gas, the number of particles unit would be molecules, of course. So this would be molecules here. Molecules. All right, so let us work this out. Taking out my calculator again. And when you work this in your calculator, you can use your brackets. It really does help when you use your brackets. All right. Now for me, my simple way of doing it is that since both of these have the same power, 10 to the 23rd power, I'm going to cancel those powers and do my simple division. Just because it's the same power, so it's 4.24 divided by 6.02 times 24 dm cubed. And the answer that I get is 16.9. Volume of a gas, once again, unit is going to be dm cubed. Awesome. I hope that gave a little bit of understanding. I have two more calculations that I'm going to do, and then we're going to try some on our own. All right, so let us go. This one here, it says we're going to be solving for the molar mass using gaseous volumes. And when we solve for the molar mass, this helps us to find out what gas is present. All right, so the question says 1 gram of a gaseous compound of carbon and hydrogen occupies 1.12 dm cube at STP. What is the molar mass of this gas? So once you see gas, volume of gas, any type of gas equation, or anything relating to gas, you're gonna use your formula. Volume, let me give it a lot of space. So volume of gas, and I want you to practice writing this equation. Just write it first. Once you see something about gas, write the equation here. Volume of gas equal mole times condition. Right, equal moles times condition. But what are we solving for? We are solving for the molar mass. We're not solving for the volume of the gas, right? So the molar mass, the only equation that mole relates to molar mass is mole. Remember, and I'm gonna go back up here so you can see the only equation that mole relates to molar mass is mole is equal to mass divided by molar mass. So I'm gonna insert it down here. So it's going to be equal to mass over molar mass. And we multiply our condition, and we're going to put back volume of gas here. Amazing. Right, now let us solve. So we're solving for molar mass. I'm going to erase this and I'm going to use a different color so that we know that this is what should be our subject. Molar mass. That's the one we're solving for. Yes. Now looking at it, we were given some information. We were given the volume of the gas. The volume of the gas we were given was 1.12 dm cubed. So I'm going to insert that here. 1.12 dm cubed. Were we given the mass? Yes, we were given the mass. 1.5 gram. Were we given the molar mass? No. We're solving for the molar mass. So I'm going to use an M here. I keep forgetting to change the colors. I'm going to use an M there. So it's M. And the condition that we were given was STP. And the value of STP is 22.4 dm cubed. And all we're simply going to do is that we're going to solve and try to make M the subject. So I'm going to remove M from the bottom here, and I'm going to carry it over to the next side. How I do that is, since M is being divided here, we simply need to multiply by M, right? When we multiply by M, it cancels, right? But whatever we do to one side, we have to do to the other side. So it's going to be M times 1.12 dm cubed. All right, now we do need to make M the subject, so we need to get rid of this 1.12 dm cubed, right? And since it's being multiplied on our left hand side, to get rid of it, we need to divide by 1.12 dm cubed. Now what I'm going to do is that instead of writing all of this on one heading, I'm going to just rewrite this so that you can see stepwise. So let me just write. So it's M times 1.12 dm cube equal 1.15 grams times 22.4 dm cube. Nice, because we already got rid of the m on the right hand side, but we do need to get rid of the 1.12 dm cube. And as I said, since we're multiplying on the left hand side, we now simply need to divide to get rid of it. Whatever we do to one side, we do to the other side, right? So we cancel here, and now we solve for m. So what is the value of m? What is the molar mass of our gas? Let us work it out. So it's simply going to be 1.5 times 22.4 divided by 1.12, which gives us 30. Right, and since we're solving for molar mass, the unit is going to be G slash mole. Amazing. Right, see, it's not that difficult. You just need to apply all of your equations. Just do one more. Let us do one more. For this one, the molecules is the subject. That's what we need to make the subject. But let's look at how the question would look. We're going to make our own equation. So it says, how many molecules are present in 5.6 dm cube of carbon dioxide at STP? Now, this is a gas. Carbon dioxide is a gas. So we're going to use our gas equation, our volume of gas equation. And that equation says volume, so I'm always writing it, volume of gas is equal to mole times condition. Nice. The volume of gas is equal to mole times condition. Right? Now what we're solving for is molecules. That's what we're solving for. How many molecules? And remember that molecules are a type of particle. And the only equation that we know relates mole and particle together is mole is equal to number of particles divided by Avogadro's number. So let us use that equation right here. So mole equal number of particles divided by Avogadro's number. So I'm going to write it. Number of particles divided by Avogadro's, I think I spelled that wrong, Avogadro number times condition and we have our volume of gas okay. So that's the new equation that we made, right? And from this equation, we can definitely solve for the molecule. I'm going to write, I remember that molecules is a type of particle. This is something that we need to remember. But I'm going to write this with a different color ink. Number of particles, because that's what we're solving for. Particles. Right, so the volume of the gas that we got, it was 5.6 dm cube. So we're just going to insert everything here, 5.6 dm cube. We're solving for number of particles. I'm just going to leave that here, number of particles. We know what Avogadro's number is. Avogadro's number 6.02 times 10 to the 23rd power. And the condition that we have is STP. The value of a gas at STP is 22.4 dm cube. And now we solve, right? We need to make number of particles the subject. So we're going to get rid of everything that is not number of particles. It's already on the top. So we can leave it there. We're gonna get rid of everything else. So we can get rid of 22.4 dm cube. How to get rid of that? Since it's being multiplied on our right hand side, to get rid of it we simply need to divide. So we're gonna divide, let me erase this. So we're gonna divide by 22.4 dm cube. Whatever we do on one side we do to the other side. So we divide this by 22.4 dm cube, but it cancels here. Alright, now on this side we still do need to get rid of our Avogadro's number, and since it's being divided by here, we do the opposite. We're going to multiply by Avogadro's number, so multiply by 6.02 times 10 to the 23rd power. Alright, and when we do that multiply, we're going to cancel it here. But whatever we do to one side, we have to do to the other side. So since we multiplied it here, we are going to multiply it on our left-hand side. So times 6.02 times 10 to the 23rd. And now we can solve for the volume of our gas. Well, not the volume of the gas, the number of particles of our gas, right? So number of particles, and I'm going to use my brackets. So I have my open bracket on my calculator. 6.02 times 10 to the 23rd power. If you want to get the power up top on your calculator, you can press XY. You get your power up top, 23. Then you close your bracket again. And now we're going to multiply it by 5.6 and divide it by 22.4. The answer that I get is 1.505 times 10 to the 23rd. And since we're solving for a number of molecules, we're going to use molecules as a unit. Molecules, which is equal to our number of particles. Nice. Now I hope this gave a little insight in solving for molar volume. Just to recap, we're just going to do a little recap. Just to recap, remember that Avogadro's law states that under the same conditions of temperature and pressure, equal volumes of gases will have equal number of molecules. Nice. And remember that we said that as volume increase, the number of molecules will increase and the moles will also increase. As temperature increase, the volume will increase because those are directly proportional, right? Note once again that our molar volume is the volume of a gas that contains 1 mole of that gas. And we have two types of molar volumes that we use. All right, we have the RTP, room temperature and pressure, which is 25 degrees, and the volume of any gas at room temperature is 24 dm cube, while the volume of any gas at standard temperature and pressure is 22.4 dm cube. And note that standard temperature is 0 degrees, right? What I would love for you to do on your own, and you can always work these out and you can reply in the comments your answers, and I would of course check once I get the chance to check. I would love it if you could solve for these, so you can take a screenshot. So this is one, that's one, take a screenshot of that one. This is one here, you can screenshot that one, and these. Alright, so thank you for watching my video. I hope you learned something, and I will see you in the next one.